Okay, so these are going to be questions or example questions involving velocity and displacement. So example question number 1. This would be like a level 1 question, a very simple question. In fact, it's going to be almost ridiculously simple at first, but that's what we want to do, is just start easy. Okay? So we're going to talk about a dog. So question number 1, a dog runs, and we'll say he runs 8 meters in, what did I say, 2 seconds. What is the speed of the dog? Well, that's pretty easy. What is the dog's speed? Now, when you answer questions, you have to go through a mental process that I want to start to set up for you. The first thing you must think of when you do your mental process is what kind of reference frame are you going to use to analyze this question. You don't necessarily write all this down, of course. You do a lot of this in your head, but I'm going to write it here so you can see the process. So the first thing you do is, what kind of reference frame is it? Well, the question doesn't say anything about which way the dog is going. And in fact, it's asking for speed, which doesn't even have a direction. So direction doesn't seem to be too important in this question at this point. We're not talking about vectors so much as scalars. But we still could say that whichever way the dog runs, we're going to assume he's running in a straight line. So we would use a linear reference frame for this. And the most obvious one would be a line going this way. And of course, that's the way the dog would run, this way or this way. And we could assume that the dog is running to the right, because we just naturally assume that anyway, right? We just kind of think that's the way it would go. Okay, so in this question, it's not as critical, but you should still consider it. The next thing you must consider is, what role will directions play in your question? In other words, are we talking vectors here, or are we talking scalars? The question asks for speed, so that means we don't have to worry too much about direction in our answer. And even the two things that are given, there's no direction really associated with that, and this is just the time. So in this case, we could probably not sweat the directions, right? And in that case, we could go back to our simplest grade 4 formula, distance equals speed times time, and we can solve the question by putting in the information. So what I like to do, or I like to suggest, is that before you jump in, you write down the stuff that you have. D, well, it said the dog ran 8 meters, so we put it there. You have a time, 2 seconds, and you're looking for a speed. And this sort of, when you look at the 3 things that you have here, that's going to help you decide which formula or what tool you're going to use to solve the problem, right? Whichever has those things in it. And so this one does. And so we go over here and we write this. Now I don't have to change this into V equals D over T, right? I just jump right in. I use this formula. I put the 8 where the D is. I put the V where V is, because I don't have a number for it. And the 2 goes where the T was. If you want, you can put brackets around it or whatever. Well, now I have to divide both sides of this equation by 2. So I divide by 2 to get V, and I end up with, I'll put it over here, V equals 4 meters per second. And that's the speed the dog is going. Now that was ridiculously simple, right? Right. Let's look at how it might change if there was a vector. Okay. Let's look at now how we would deal with that if there was a vector. Let's say the dog ran 8 meters west in 2 seconds. And then what is the speed? I'll just write what is V. Well, I better write what is velocity. Okay. What is the velocity of the dog? Well, it's all the same sort of thing. We start with what we got. We got a D. Now this time, it's not a distance, it's a displacement, right? So it's not the same thing. And so somehow I have 8 meters west, but I have to translate that into math. So that will become -8 meters when I want to use it, right? because the negative sign means west. Our reference frame is a line west, east, plus, minus. So negative numbers mean west. So that's what I have to do when I do my math. I change that into -8. And then the time is still 2 seconds, and the V is what I'm still looking for. Okay? So I can still use my equation, D equals VT, and it would be -8, because this now is a displacement, and this is now the velocity, see? And this would be V times 2, again. And really, the only thing that's different is I'm going to end up with -4 is the velocity. And that means that the velocity then is 4 meters per second, and I'll translate the negative back into west, like that. So that's how it would change, the negative sign. Now, if that was east, it would look identical to the first question, wouldn't it? Because it would all be positive. I chose west on purpose so you could see the negative sign. But that's basically how you would address it if it was a vector, with the direction in mind. Okay, let's do another example. You good with that one? Still copying? Maybe move it up a little bit. Okay, now let's do another question altogether. This question is going to be, how am I going to word this one? Let's make it a cat this time. A cat moves from a position 8 meters away from you to second position 20 meters away from you. In 3 seconds. Then we want to find the speed of the cat. Okay. This one is kind of the same, except there are 2 positions. So I'm going to describe the 2 positions as D1. Position and displacement are kind of the same thing, right? So this would be D1, and it would be 8 meters away from me, or you. And then D2 is going to be the position that is 20 meters away. And then the time involved is 3 seconds, and I'm looking for the velocity, or the speed. I guess in this case it's speed, right? Yeah, speed of the cat. So again, we're not worrying too much about directions. Okay? I can bring that down there. Now we can see it all. Well, when I look at the information that I have here, it makes me think of the version of my formula that looks like this. The change in displacement over the change in time. And we shortcutted to this, remember? We talked about how we could kind of make that a shortcut. So if I do that, it's 20 minus 8 divided by 3, which comes out to 12 over 3. I just kind of jumped over here, and that's going to be 4. So this is kind of coming out to 4 as well. So there you see the speed of the cat. Pretty straightforward, pretty easy to do once you get the hang of it. Okay, that's easy. Level 1. Let's step it up a notch, and let's talk about how things might get a little more complicated. Let's do a graph. Let's say the question shows up as an actual graph. So here's a question where they give you this. And there's a time here, and this is a graph of displacement and time. And here is the actual line on the graph. It goes from here to here. Okay? And they give you some information. They tell you that this point right here is 60. And they tell you that this point down here, here is 10. And then they give you more information. I'm going to write it in a different color, just so that it shows up. They take a spot right about here, and they call this 4. And then the same spot right over here is 72. And then they call this spot up here just B, because that's kind of the question. And what the question asks is, what is the displacement of the object when it is at B? So the red line is where the object is. It started at 60 and it made a little trip and ended up at B. We want to know what the displacement is at B. So now we have to kind of pull the graph apart to figure out what it's telling us. And the first thing you should do is look at the graph and figure out where your answer is, or where it lies. In other words, what is the displacement of the object at B? Well, that means you have to go over here and look at B. So we want to know something about this. And the displacement, of course, is on the side of the graph. So what we're actually asking is to find out what this number is right here. That's our magic number. That's the answer to our question, right? So now we know that, we can sort of set about trying to find it. I'm not sure what this is. We can set about trying to find it, and hopefully we can figure out a way to get it. So let's pull apart the graph. Let's think, okay, what have we got here? Well, we've got, I'll do it in blue so it shows up. We've got a D1, actually I'll do it in green because we're going to use those numbers. The first position of the object is at 60, right? You can see that right here. And the second position of the object, well, I don't know what that is. That's kind of my thing I'm looking for. That's a B. But I do know that there's a time associated with that. Now there are two times on my graph. There's a 10 and a 4. But if I'm talking about B, obviously it's the 10 that goes with B. So I'll choose 10 here. Okay, well that's not enough. It also would be kind of nice if maybe there was a V that I could use, because then I could see where I'm going, right? Then it's kind of like the other question, and I can see the answer. So you look at this and you say, gee, too bad they didn't give me a V. And then you say, wait a minute, why did they give me those blue numbers? And then you realize, oh, maybe those blue numbers might help me get the V. Maybe they're for a reason. So you start to think about what the V is on the distance time graph, and you realize it is the slope, right? So you think, oh, wait a minute, V is the slope. So this is what's going on in your head. V is the slope. So maybe I can get a slope. And those two numbers in blue might be useful. So then you go over here, and you look at the fact that there's a little triangle you can draw. And if you draw it here, you can see that there's a rise of how much? Well, that would be 12. And there's a run of 4. So you can calculate the slope, rise over run, 12 over 4, it's 3 meters per second. That is now the V. So you figured out the V. Put that number 3 right there. Wonderful. Now, there's two ways you could approach it from here. You could just plug in the numbers and figure it out. Right? So one option 1 would be, okay, I'm just going to do this now. I'm going to go V equals D2 minus D1 over T. Right? That's our formula. I'm going to put 3 equals D2 minus D1 is 60, and the time is 10. So if I continue that beside here, then multiply both sides by 10, right? So you get 30 equals d2 minus 60. Good. And then move the 60 to the other side. 30 plus 60 equals d2. And so that spot is 90. So now I know where it is. This is my spot, 90. Figured it out. That's a little tougher. Not quite as obvious what to do. Often in physics you're faced with a problem where it's not obvious what your method should be. And you have to kind of tease the question a little bit and play with it to figure it like a puzzle more than actually a question. Now there's another way you could solve this. Instead of doing this, just to show you the alternatives, if you go back to graphing, you found the slope was 3, right? The slope of that red line. Well, the slope of a line is the same. This line has the same slope all the way along. So you could pick another triangle right here, and you could do the slope there. I'm going to scribble on top here. The run is 10 for that triangle, right? 10, the whole thing. And the rise happens to be this much that you kind of want to know about. So if you figure out that, and I'll just come down here, if you do, the slope has to be 3 because we already figured that out, and that has to be rise over run, then what you end up with is 3 equals the rise, whatever that is, divided by the run 10. And so that means 30 is the rise. So this is 30, but you already know that the bottom piece here is 60 because that's where it started. So then the top piece must be 90. 30 plus 60, add them up, and you get back to your 90. So you see you have alternate solutions and lots of different options, and you can choose any one that works for you. The beautiful thing about physics is that there are often 3, 4, 5 different possible solutions to a problem, but they all arrive at the same answer. Okay? So any one of those would work. So that's more of a higher level 2 question, because you have to think a little more about what everything means. You have to remember things like, oh yeah, the slope is the speed on that graph. And you can't just follow the math and do it. It's not what I call a plug and play, like the first one. You just plug in the numbers and go, and you get an answer. Here you've got to actually think a little bit about what you're going to do first. Let's do another one sort of requires you to do a little bit of thinking, but not much. So another example. Okay, 2 runners in this question. Bob, and he can run at 4 meters per second. And Stacy, she runs at 6 meters per second. So obviously she's faster. Okay. Stacy is 100 meters away from a tree. She gives Bob a little head start, because obviously he's a bit slower. So she says, okay, Bob, I'll give you a head start of 20 meters. And then they race to the tree. Who wins is basically the question. Stacy is faster, but she has to go further. Bob is slower, but he doesn't have as far to run. So what I'm going to do is just pause for a second. I'm going to let you see if you can figure this one out on your own, and then we'll take it up. Okay, so what I would probably do here, my first inclination of how to solve this question would be to do it this way. But there's many different options. But here's what I would do first, I think. I would just make 2 little summaries. I would put Bob over here and Stacy over here, and just see what I knew about each one, right? And so I know that Bob has a certain distance to run. I'm going to put a little b there, just so I know that's for Bob. And then he would have a time for Bob, and speed for Bob. So I can just kind of put those things in. Now Bob has a head start, so he only has to run 80 meters, right? Because he's at 20 meters ahead. So he's going to run 80 meters. And the time, of course, I don't know his time. That's what I'm trying to figure out. But I know he runs 4 meters per second. So now I can easily calculate for Bob, D equals VT, right? So 80 equals 4T. And so if you divide by 4 on both sides, 20 seconds for Bob. And then I do the same thing for Stacy. And actually this question doesn't seem all that hard after all. But let's not call him that. Let's call this D for Stacy. She's going to run the full 100 meters. The time for Stacy is what we're after. And the speed for Stacy is 4 meters per second. No, 6 meters per second. So for her, D equals VT, and we've got 100 equals 6T. If I divide both sides by 100 divided by 3, a third is 33.333. So if you divide by a 6, that's just another half of that. So it's about 16 and a half-ish, give or take. So we'll put 16.5-ish here, and that would be the time for her. And obviously she gets there first, so she would win. That's one way of doing it. It's a pretty straightforward and it's pretty simple. The other way to do it could be to draw a graph of what's going on and see what you could come up with on the graph. Let's try that. So if we were to draw a graph, I think my arm keeps rubbing there. We draw a graph like this and like this, time and displacement, right? Now, we could do a different kind of a graph. Like it doesn't have to be displacement. It could be velocity, right? But we haven't learned yet how to deal with the velocity graph, so let's try the distance graph right off the bat. And let's put 2 different colors. So here's Stacy, who starts here, and she's going to run to the tree, which is 100 meters away. So I'll put 100. And she's going to do it in a certain amount of time, but I don't know her time. So when you don't know the time, you just pick a spot and you put time for Stacy. And we'll just let it go. We'll let the math tell us what that number should be when the time comes, you see? So that means that she's going to run, and she's going to get this far and this far. So basically her line is this one. So there's Stacy. But I also know something else very important about this line. I know that it has to have a slope of 6, don't I? Because I know that the slope is 6, because that's the speed, now I know what TS is. Slope is rise over run. So I can figure out TS by doing rise over run equals 6. So 100 over the run equals 6. So that means that 100 divided by, what you would do is you would multiply both sides by the run first, and you get this, 6 times the run. And then you divide both sides by 6. So 100 divided by 6 is the run, and the run would be, what we said before, 16.5, right? Equals the run. And the run, of course, is the time. That's what the run represents on the graph. So that's perfect. Okay? So we could use the graphical method that way. And then we could go back and on the same graph, we could draw a graph for Bob in, say, green. Now Bob runs at 4, so, and he starts in a different spot. He starts here, say at 20, right? He has a 20-meter head start. And his line would be a little bit less sloped because his slope is 4. So I'll just draw him something like this. And then he'll get down here, so I should have made my graph a little bigger, I guess. That's not a problem. Oh, by the way, when we do graphs like this in physics, this is how you do them. You sketch them. You don't worry about graph paper and measuring everything perfectly. You just sketch like I'm doing right here, and you only put in the numbers that matter. You don't worry about drawing all the ticks for the scales or anything like that. These are sketches, and they work. Okay, so this is when he would get to the finish line, which is still 100, right? He's still getting to the tree. So it's the same line across the top. So what I need to do for Bob is just figure out what this time is. Bob times for Bob. And I can do that if I go like this, I can do a rise and a run. That's the rise. And then down here is the run. So I can do the same thing for Bob. And 4 is the rise over the run. Well, his rise is 80, and his run is, I don't know, time for Bob. So it would be 4 times the time for Bob equals 80. First multiplied by the time, right, on both sides. So it comes up, and then divide by 4, and there's where I get my 20 for Bob. So the graph could also work. Because remember, those equations we're using actually come from the graph, right? Okay, so that's a very sort of level 2-ish, maybe even a level 3-ish type question. It would be a low level 3, because it's pretty easy once you get the hang of it. But there's a lot of things to think about there, to put a lot of things together and use stuff like slopes that you maybe wouldn't have thought of. Okay? So that's where we'll stop.